Okay, let me introduce you. Dan Stewart, who's doing the soils presentation today, has a master's degree in environmental science from Virginia Tech. Then since 2003, he's worked as a soil scientist for the Northern Virginia Soil and Water Conservation District. His responsibilities include updating the county soils map, EGAD, outreach to the public, technical consultation to county agencies, soil and stormwater research, and erosion and drainage assistance to Fairfax County homeowners. So I guess we can see that Don hits the ground running every day. This is a pretty wide area to cover, and we are delighted that you could be with us today. And I'm going to turn the program over to you, Dan.
Okay, thank you, Kim. Let me share my screen here. All right, can everybody see my presentation there?
I think yes.
Okay. All right, well, we'll get started. So this is entitled The World Below Our Feet. So, as gardeners or as folks who are interested in gardening, you're probably aware of some of the stuff that I'm going to go over, but hopefully I'll add a little bit of detail and interest to the soil world, because if you want a healthy garden, if you want healthy trees, healthy lawn, you really have to look at what's going on below the ground. So soil is a very, very rich ecosystem. And what grows on the top is very obvious, and that's what we're looking at. We're looking at our blooms, our flowers, our trees, our shrubs, our vegetable crops, or fruits that we're growing in the garden. But none of that is really possible unless you start looking what's going on below the surface. And what's below the surface is, while extremely important, is not necessarily all that obvious because it's out of sight. Oops. But there's a tremendous amount of activity just below the ground surface, and much of it is beneficial to what's going on with your plants themselves. It can be detrimental as well, too, depending on what's happening. Here we've got some photos of just a small fraction of the things that you might find below the surface. So on the left, we've got some of our invertebrates, our kind of bordering on the edge of microscopic mites and springtails and other small insects that live in the soil. Some of these are microscopic. And then on the right, we have the real meat, if you will, of the soil fauna, and that's the bacteria and the fungi. And of course, we don't always appreciate them like we should, because these are all microscopic. We won't be able to see these with our naked eye, but there's tons of them, literally tons of them down in the soil. And they do a tremendous amount of beneficial work in the soil that helps us grow those healthy plants. So I wanted to start off kind of with a concept. This isn't so much of a scientific thought. It's just something to sort of help you wrap your head around what soil really is. So conceptually, I like to think of it as the skin of the earth, but we can also think of it as the intersection of the three general spheres of matter. So we've got our hydrosphere, which is all of our water, from the Atlantic Ocean to something as small as little droplets of microscopic droplets of water vapor up in the air, to our deep groundwater reservoirs, to our streams, our rivers, and our lakes. All that water put together, ice or liquid water, is our hydrosphere. We've got our lithosphere. Litho means rock. It's all of the solid rock, as well as the rock that's beginning to pulverize and break down into smaller particles throughout the world. No matter where you are, if you dig down deep enough in the ground, you will eventually hit bedrock. So there's a tremendous amount of rock underneath our feet. And in some cases, you go to a mountain, you go to a steep slope, sometimes that rock is popping right up there at the surface. And then there's the atmosphere above us, which is pretty self-explanatory. It's the air above our head. Right at the skin of the earth, where all three of those spheres mix together, that's where you get soil. And that's an important concept to understand, because we think of soil as a solid, and there are certainly solids in soil, but equally important are the air and the water constituents of soil. So think of soil as really being that mix of rock, air, and water. And you can kind of see this in action when you actually look at a pie chart of what soil is. It's actually a lot less solid than we think. And I should kind of caution this by saying this is healthy soil. We don't always have healthy soil in the urban environment. But if you have a nice healthy topsoil, what you're really looking at is a substance that's only about 50% solid material. A quarter of the volume of that healthy topsoil will be taken up by air or gases, and another quarter will be taken up by water. And of course, these proportions can change after a heavy rainfall. There's going to be a lot more water in there. Middle of July during a drought, we're going to have a lot more soil air. But generally, throughout the year, we'll see this 50% solid, 25% air, 25% water by volume ratio in our healthy soils. If we were to break that down a little bit more, mineral materials in our soils make up about 45% of the volume of our soil, and the organic material makes up about 5%. A small portion, but a very important portion. And this is a very good dispersion to have in your soil because obviously you need to get air and water down to your roots in order to get the plants to live and thrive. But you also have to have a substrate that's strong enough that your larger trees aren't going to fall over every time we have a gust of wind. And that's what this dispersion of material in soil really gives us. But even though soil solids make up less of the soil than we probably assume, they're still very important. And oftentimes when we're describing soil or why soil is different from one spot to another, we're really talking about differences in the soil solids. So let's talk about those soil solids a little bit. We can break down the 50% of soil that is solid material into two general fractions. We've got our mineral fraction, and then we've got our organic fraction. So the mineral fraction is very basically sand, silt, and clay. I should have added organic matter in there too as well. The organic fraction is our living material and our dead material. Sand, silt, and clay, what are those? Probably terms you've heard before. And it's actually a fairly simple concept. There's lots of different types of sand, lots of different types of silt, lots of different types of clay. And those differences within each of those three categories relates to the mineral composition of those unique types of sand, silts, clays. We're not going to get into that at all because that gets very confusing very fast. And I can't even say that I know it really well. But when we're talking generally about sand, silt, and clay, what we're talking about is differences in particle size. That's it, just the size of the particle. You can have a material that has the exact same chemical composition, and a larger piece of that material will be considered sand, a smaller piece will be considered silt, and even smaller piece will be considered clay. So between sand, silt, and clay, you don't necessarily have to have a chemical change, but you do have to have a size change. So there's different ways that these particles are broken down, but generally as gardeners or people interested in plants, we use the US Department of Agriculture's definitions, and they define any mineral particle with a diameter between 2 and 0.05 millimeters to be a particle of sand. Silt would be any mineral particle with a diameter between 0.05 and 0.002 millimeters. So we're starting to get into some really small stuff now. And then clay is any mineral particle with a diameter of less than 0.002 millimeters. And that's kind of an odd number. What does that mean? Obviously, 0.002 millimeters is very small. But that's also it's akin to saying it's 2 microns. 0.002 millimeters is the same as 2 microns. A micron is a millionth of a meter. So imagine your meter stick, it's a little over 3 feet wide. If you were to take a tiny little knife and somehow slice that 3+ foot wide meter stick into a million equally sized slices and put 2 of those slices together, that width would be the size of your largest particle of clay. And clay can get a lot smaller than that too. I saw another good presentation years ago from a master gardener in Arlington, and she was saying, if you've ever go to a Washington football game, the stadium is akin to a particle of sand, your car is akin to a particle of silt, and the parking ticket on your windshield is like a particle of clay. So even though these all things seems very small to us, the differences between sand, silt, and clay are really quite large in terms of their size, even though to us they all seem fairly small. So that's the mineral fraction. That's 45% of the soil. The organic fraction is 5% of the volume of the soil, and this consists of living material and dead material. So the beetle, the earthworm, the roots of the plants, all living material within the soil, we actually consider that to be part of the soil. So when we say that a soil has X amount of organic carbon or organic matter in it, we're actually including that living stuff as part of that number. The other portion of the organic fraction, and then of course there's all the microscopic stuff, the bacteria, the fungi, the smaller invertebrates. For every teaspoon of healthy topsoil, it's estimated there could be anywhere from 100 million to 1 billion bacteria living inside. For the fungal roots, which is the picture you see down in the middle right there, they're multicellular. They look just like tiny, tiny little threads. If somehow we were to extract all those roots from that teaspoon of healthy topsoil and lay them end to end, they could stretch anywhere from about 40 yards per teaspoon to 40 miles per teaspoon. So there's a lot of stuff living in the soil Most of it's invisible to us. That's the living portion of the organic fraction, and then there's the dead portion, which most visibly to us is the leaf fall that we see in autumn. But of course, there's other portions of dead material that enter the soil at all times of the year. Every time an animal defecates, that gets added to the soil, dead organic fraction. Every time an animal dies, the carcass gets returned to the soil. When you cut your grass and leave the grass clippings on the surface, that gets returned to the soil as dead organic material. And that's what feeds the living organic material. That dead organic material is the food source for the living organic fraction within the soil. Now, one very important thing that you may hear about a lot when you're working with soil, when you're talking to people about soil, is something called the soil's texture. It's a good term because it simply means the percentage of sand, silt, and clay in a soil. So the mineral fraction determines the soil texture. And the soil texture, I think it's a good term because basically it determines how the soil feels, but that's not why it's important. It's important because the soil texture, that percentage of sand, silt, and clay, has a very large effect on the ability of the soil to retain water, to retain nutrients, and to infiltrate material, meaning to pass basically air and water from the surface after a rainfall down into the rooting zone of the soil. And we'll see some general patterns form when we're talking about texture and the ability of the soil to hold nutrients and to infiltrate water and air. So again, these are very simplified graphs, but basically if you're up here at water holding capacity graph, let's say you start here at the nexus of the two axes and you start working your way to the right down the x-axis. It's almost like these are sort of synthetic soils. If somehow we were able to change the texture, so we start off with 0% clay and then start adding more clay until we get up to basically 100% clay, pottery soil. What would happen as we add clay and reduce sand and silt to the water holding capacity of that soil? Well, the general pattern is the more clay we have in our soil, the greater the ability of that soil to hold water. Clay can hold a lot of water within soil. And the exact opposite pattern holds if we were to do the same thing but add sand. So we start with 0% sand and we start working our way along the axis until we get to a soil that's pretty much 100% sand, which is be closest to what you can find at the beach, basically. So as we get sandier and sandier and sandier, the ability of that soil to hold water reduces. More sand equals less water holding capacity. We see the same pattern with nutrient holding capacity to the right. We take that same soil, we start adding clay until we get up to that really sticky, high clay pottery type soil. The ability of that soil, as the clay content increases, to hold nutrients also increases. But if we were to do the opposite, if we were to take the soil and start adding sand and subtracting those fine particles of clay, we would find as that sand content increases till we get to our beach sand over here, the nutrient holding capacity decreases. However, the odd thing is, for infiltration capacity, the relationship flips. We add more clay. Clay, as you probably know, is kind of sticky, dense feeling stuff, tends to gum up the soil. It prevents water and oxygen from the surface from quickly passing into the soil. So the infiltration rate, infiltration capacity of the soil reduces as we increase the clay content. And with sand, as the sand increases, unlike the water or nutrient holding capacity, the sand increase will increase the infiltration capacity. More sand equals faster entry of air and water down into the soil. Now, this is a shame because we want a soil that has the ability to hold a lot of water, the ability to hold a lot of nutrients, but has good infiltration, because if water and air can't get into the soil, there's no way it can be held in the soil. But what this is telling us is that we can't really get all three of those beneficial traits by the texture alone. If we have a sandy soil or a clay soil, we can get one of the three or two of the three, but not all three. And in fact, the clay and sand will actually hurt us in other categories. But in some ways, this doesn't really much matter because texture can't really be practically changed. I mean, you could theoretically pay somebody to bring in 60 dump truck loads of clay and till that into your soil in the top 4 feet, but you're not really going to do that, nor will you do that with sand. So you're sort of stuck with the texture that you have. If you have a sandy soil, you're kind of stuck with the sandy soil. Same thing with clay. So it's best to work around the limitations that a not so great texture will have for you. And we'll get into that a little bit later. So that's the mineral fraction. Now the organic fraction is very interesting because just like the mineral fraction, it has a large effect on the water retention ability of the soil, the ability of the soil to hold nutrients. the ability of the soil to infiltrate air and water, but it also really affects the nutrient cycling in the soil, the ability of that soil to sort of move nutrients around and make them available to plants. And the real kicker is, unlike the soil texture, you can change the organic fraction, the quality and the volume of the organic fraction through good soil management. So if you have a soil that seems to be lacking something, you don't really want to focus on the texture. What you want to focus on is changing the organic fraction for the better. So what does the organic fraction do? Well, it really depends on which portion we're talking about. Is it the dead organic matter or the living organic matter? Start with the dead. The dead organic matter is the base of our soil food web. So just like there's a very important food chain occurring on the surface that we are a part of, there's an equally important food chain occurring just below the surface in the soil. So we consider these dead leaves, dead animals, manures, other dead organic matter to be basically the lowest level food source that really powers that whole soil food web. And the soil food web is complicated, but here's a fairly good simplified diagram of what it looks like. This can't show all the connections, of course, but there you have your organic matter down at the bottom, which sort of is the nexus of all the energy that flows through this soil food web. Organic matter, of course, is added by leaves, by dead grass, but it also is added by plant roots. Roots actually exude a lot of organic matter directly into the soil. And the theory is they probably do this in order to help the soil food web power up, because that helps them in the long run receive the nutrients that they need. So there's a lot of direct inputs from the plants, as well as indirect ones like leaf fall, dead trees and branches falling down and such. So the dead organic matter is the base of the soil food web. The living organic matter is basically the processors. They are the organisms that take that organic matter and turn it into a usable form. And really the most important ones are what we call collectively the decomposers. This would be our bacteria and our fungi, those hundreds of millions to billions of little tiny microscopic microbes that are living in the soil. They're generally the ones that first attack that organic matter and slowly decompose it and break it down into soil humus. And luckily for us, as they do that, they're sort of messy eaters. So they do it for their own purposes. That's their food source. They need energy and organic carbon in order to power their life cycle, to grow, to reproduce, to keep their populations going. But they also release a lot of nutrients out into the soil as part of this decomposition process. And also they're eaten by other higher level predators within the soil food web. And when that happens, that also tends to release nutrients out into the soil, some of which is then available to the plants. The living organic matter also plays a very important role in collecting nutrients. So the first couple speakers mentioned, or at least Alonzo did, I know, mentioned mycorrhizae, which may be a term you're familiar with or not. Here's a picture of what mycorrhizae looks like. Here's a pine seedling that's been inoculated with some mycorrhizae. The dashed lines are basically circling the area of the pine roots. All those other little fine roots you see in the soil outside of those dashed lines, those are mycorrhizae roots. Mycorrhizae is a class of soil fungus that actually invades and infects roots, but in a beneficial way. So this fungus gets into the plant root, and it sends its own fungal roots out into the soil, which in effect greatly increases the reach of the root mass of that plant. Those fungal mycorrhizae roots reach out into the soil, and these very fine roots are very efficient at extracting water and nutrients from the soil. They bring that water and nutrients, they give it to the plant, and in return, the plant gives the mycorrhizae food, carbohydrates, organic carbon. So the plant feeds the mycorrhizae, and in return, the mycorrhizae collects nutrients and water to feed the plants, and it's this nice beneficial relationship. I would say almost all of our big woody plants, our shrubs, our native trees have a mandatory relationship with mycorrhizae. They really need those mycorrhizae in order to live. There are a few species of plant, unfortunately, I couldn't name which ones they are. I don't know them well enough, that don't require mycorrhizae, but the majority of our local plants need this relationship with mycorrhizae in order to live. So if you see them growing in your landscape, chances are you've got, at least a pretty good population of mycorrhizae in there too. So that's sort of nutrient collection. There's the mycorrhizae if you want to see it spelled out. And then the living organic matter is very good at creating soil structure. which in addition to texture is one of the most important soil physical characteristics. Soil structure basically refers to how the soil physically clumps together. And I'll get into some details on the importance of soil structure in the next slide, but it really affects the ability of air and water to pass down into the soil. So moving back to the effects of texture slide that we showed. Well, again, texture affects the nutrient holding capacity. If you have a really sandy soil, it's very hard to hold on to nutrients in any high degree. However, if you've got a really good, healthy pool of soil organic matter and the microbes to break them down, well, the texture doesn't matter that much because it's the organic matter fraction, both the living and the dead, that are really powerful in cycling nutrients and cycling organic material and processing it in the soil. So that if you have this great pool of microbes and other soil fauna, and you have a good source of organic matter feeding that soil food web, it doesn't really matter if you have a sandy soil. You can work around the limitations of the texture. So I mentioned we were going to talk about soil structure next, and that's very simply how the soil solids are arranged together. How do they clump? We find that naturally soils will tend to clump into little aggregates that we in soil science call PEDs. So if you ever go to Virginia Tech, Virginia State, Maryland, any of the land-grant universities around here that have an agriculture school, you'll see that the professors of soil science, their official title is pedologist, someone who studies PEDs, because PEDs are sort of like the smallest level of soil that we can see with the naked eye, those little clumps of soil that you can dig out of your garden. Soil is kind of like a bowl of cereal if you really look at it. It looks solid from a distance, but if you get up close, you'll see it's made up of these little discrete clumps, just like your bowl of cereal is made of discrete flakes and O's. And they have these kind of general shapes. And generally speaking, a good texture, especially up in your topsoil, is going to be right down here, letter F, which is our granular structure. It kind of looks like grape nuts cereal, both in terms of its size and its shape. So we get down deeper into our subsoil, into the clayier subsoil that we naturally have in Virginia. You have this blocky structure, which looks just like the granular structure on top. It's just bigger. This is rare to see, the A and B structural types. This is called prismatic and columnar, but you will find these in a few spots where we have naturally shrinking swelling clays, the types of clays that swell up when they're wet and shrink down when they're dry. They tend to, over time, through many shrink and swell cycles, create these kind of tall columns of soil. And we'll also find a lot of this platy soil, especially in urban areas where the soil has been compacted. And this is often formed when a nice, loose, well-structured soil gets squished underneath a heavy weight. The importance of soil structure is that as these soils clump together into these PEDs, you'll find that micropores, small pores, naturally form within the PEDs, and macropores form between the PEDs. So what separates one PED from its neighbors is a macropore on either side. And those macropores sort of act like the highways of the soil that allow air and water to get from the surface down into the rooting zone. The micropores are more like those small capillary wicking pores that hold onto the water as it passes through and hold onto it for a longer term. And organic matter is really essential to forming soil structure. What we consider to be good soil structure is well-formed PEDs that are fairly waterproof. If we have a heavy rain and the rain passes through our pores and it causes all of the PEDs to just sort of disintegrate, that soil is going to get clogged up every time it rains, and that's not doing us any good. Organic matter is a natural glue, especially as organic matter breaks down. Some of those breakdown products are naturally gluey type materials, and a lot of them are waterproof gluey type materials. They tend to coat the soils and allow for the formation of these fairly well aggregated PEDs that hold together well, but also do not disintegrate when we have really wet weather. So organic matter is one of those very important natural glues that allow for the soil to clump together into these PEDs and stay together regardless of the weather. So if we have a well-structured soil, it's got nice, well-formed PEDs with pretty big macropores in between, and it's also got a good amount of organic exudates and organic decomposition products which coat those PEDs and make them fairly impervious to water, fairly water tolerant. If we have a big rain, most of that rain is going to quickly percolate down into the soil and get down into the rooting zone. If on the other hand, we have a compacted soil, which results when we take this nice, well structured soil and then compact it and squish it under a heavy weight. We get these flat plates that kind of interlock tightly. There is still some pore space in between them, but a lot of the pore space, especially the macropores, have been squished out. So there's just not as many pathways for water and air to get in the soil. And we have that same rainstorm. What happens? A little bit of the water gets into the soil. A lot of it stays up at the surface, where it can either cause puddles if the surface is flat, or surface runoff if you have stormwater runoff, if you have a little bit of slope to your land. So ideally, that's why we want to have that good soil structure. It gets the water into the soil, down where it's needed, and prevents a lot of stormwater runoff. So again, going back to the effects of texture, if we have really good organic matter content, chances are we're going to also have a good soil structure, and this allows us to have good infiltration. So the textural effects don't matter so much. If we have that really clayey soil, which ordinarily would be very tight and gummy and wouldn't let water in, if we have a good amount of organic matter in that clayey soil, we can still get good infiltration in the clay soil, and it's sort of like texture, again, takes a back seat. The bad effects of texture can be greatly, greatly nullified. And then there's finally the organics and its effect on the water holding capacity of soil. So the total amount of water that's held in soil is not that important. It's the amount of water that's available to plants that is important. And that is the water that's held between two states, the wilting point and the field capacity. Wilting point is fairly obvious from its name. That's the point at below which, if the soil gets drier below the wilting point, the plants start to wilt. The interesting thing is, if you look at the textures, here we have a sandy soil, here we have a loam, which is a mix of sand, silt, and clay, and here we have a clay soil. So basically, we're going from a coarse soil to a very finely textured soil. You'll see that the wilting point increases greatly. That's because clay can hold a lot of water, but it's greedy. It holds it very tightly. The water kind of bonds in spheres to the surfaces of clays, and clay holds that sphere of water very, very tight. So even though there may be a ton of water still in your soil, you might see your plants wilt in a clay soil because that water is held too tightly and the roots just don't have the energy to suck it off the surfaces of the clay. On the other hand, if we have a sandy soil, the wilting point is extremely low. Sand holds water very loosely, so almost all of it's available to plants, but there's just very little of it available at all because sand holds very little water in total. The field capacity is basically the total amount of water that the soil can hold against the pull of gravity. If you ever bought a dry sponge at the supermarket, you put that sponge under your sink, you drip water on it until it expands. Eventually, you add enough water, water's going to start dripping out of the bottom of that sponge. You turn the faucet off, and after about 15 to 20 seconds, the dripping stops. That basically is a sponge that's at field capacity, meaning it's holding the maximum amount of water that it can against the pull of gravity, that the water that's in that sponge is more attracted to the sponge than the pull of gravity. That's what field capacity is. And we usually get field capacity a day or two after a real soaking rain. So it's the maximum amount of water that the soil can hold before gravity just starts pulling it out. And that's what we consider to be the maximum amount of water that's available to the plants. The real plant available water is the water that's held between the wilting point and field capacity. So the further these two bars get apart from each other, that means there's more available water to the plant. So you can see, even though clay holds the most, it doesn't have the most plant available water because the wilting point's so high. Sand has the least plant available water because it just doesn't hold very much water at all. Loams have the most. If you've got a loam, you probably have pretty good water holding capacity. But again, with texture, there's not much you can do to change it. However, regardless of the texture of your soil, if you add organic matter, the effect generally is to greatly increase the field capacity. So we move from here all the way up to here, while just slightly increasing the wilting point. We go from here just up here. And what this tends to do is separate those two bars, no matter what your original texture was. So whether you're starting with a clay, a loam, or a sand, if you add good organic matter, it'll tend to increase significantly the plant available water. And the reason for this is organic matter, especially soil humus, is a lot like clay in that it can hold a lot of water, but unlike clay, it holds it loosely. It's not greedy. It shares it readily with the plants. So add organic matter and you generally will increase significantly the volume of water that your soil can hold that is available to your plants. So again, going back to the effects of texture, we've got water holding capacity, and we see with the high sand content, you generally have less available water. Clay can also have some issues, but if you add organic matter, you can kind of nullify those bad effects of texture. What does soil look like? Well, it comes in layers that we call horizons. Up at the top, we've got our O horizon, which is just loose organic litter on the surface. We've got our A horizon, which is what people call topsoil. Around here, naturally, we only have about 2 or 3 inches of it. It's not very thick in Virginia, but that doesn't mean it's not healthy or important. It is very healthy. Sometimes we'll find an E horizon down below. I'd say less than 50% of the time, but that's sort of a leached layer. There's a lot of natural acids build up in the soil, and over time they tend to leach all these things out of the E horizon, and it leaves behind of this gray, washed out looking layer below it. We've got the B horizon, which unlike this photo in Virginia tends to be very thick. If you have red Virginia clay, what you're probably talking about is your B horizon. This is where the clay deposits. It forms up top, but over many hundreds or thousands of years, rain pushes that clay and lodges it down in the B horizon. And the B horizon will actually get thicker and thicker as that soil ages. Below that, we've got a C horizon, which is kind of a transition zone. It's usually where the clay content starts to drop out and the soil starts getting sandier and grittier. And then R, bedrock down below eventually. And the depth of bedrock can vary greatly. If you live in Manassas, it's probably about 3 or 4 feet below the surface. If you live around Woodbridge, it might be 500 or 600 feet below the surface. So there's a great variety. But really, when we're talking about soil health, the A horizon is the most important. And even if you only have 2 or 3 inches of it, which you probably do in most soils around here, the A horizon is the biological powerhouse of the soil. It's got that dark color because it's got so much soil humus in it, because it's right there in the rooting depth of those plants. And it's also receiving all that leaf fall and other good organic matter from the surface. So this is where you find the really high concentrations of soil microbes and a lot of soil nutrients and nutrient cycling and organic matter. So a healthy soil plant system will feature an A horizon or topsoil with lots of organic matter. And you also want to have a nice granular structure. And if you have those things, you're probably going to have a very healthy population of microbes. That large microbe population will break down the organic matter and in the process release nutrients, some of which will become available to the plants. You want to have that nice granular structure, loose, but fairly water tolerant, so it doesn't dissolve in water. And this allows in lots of oxygen and water from the surface. It allows it to readily percolate down into the soil and get to the roots and to the microbes. And as the water percolates down, it dissolves some of those nutrients that were released by the microbial breakdown of organic matter. Roots can only take up nutrients that are dissolved. Roots only take up oxygen and water from the soil. So any nutrients that they take up have to be dissolved in that water first. So you need that water to get down into the soil to dissolve those nutrients and make them available to the plants. And it's a virtuous cycle. Well-fed plants that have lots of nutrients that they get from their A horizon will put on more growth. And as they grow more, they're going to add more organic matter through leaf fall, through root exudates down into the soil and feed that cycle and keep it happy and healthy. Now, let's talk about urban effects. So, when we develop soils, when we build houses, when we put roads on top of it, when we put the shopping centers and offices, and it causes a lot of changes in soils, and basically all of them from a soil health perspective are bad, unfortunately. One of the big ones is compaction. When we run over soil with heavy equipment, we tend to squish it down, make it much more dense, and squeeze out a lot of those important pore spaces and pulverize a lot of those good soil PEDs, those good soil structural units that we really want to have. And what's left behind is a much denser, less porous type of soil. So here's what might happen in a typical soil as it's developed. We've got 25% air, 25% water, and 50% solids when we start. We start developing it and we run over it with that heavy equipment and we squeeze out the pore space that allows for that 25% air and 25% water to exist. Less pore space means the soil is much more solid now, and there's just not the space we need in order to get the gas, the air, and the water down in there like we had before. Excuse me. So we have a significant loss in pore space as soil is developed, and a significant increase in density. They go hand in hand. And this reduces the ability of air and water to pass from the surface down into the ground. So this causes stress on the plants, but also a significant increase in stormwater runoff. And we've got a lot of that platy structure around in our urban environment. And when it rains, just that platy compacted soil does not allow nearly the volume of water to percolate down into it as the natural soil would have that was there before it was developed. And I call this impervious light. A compacted soil is not an impervious surface. It does allow some water in, but it can be a significant reduction in the amount of water that percolates down compared to a healthy natural soil. And this can be confusing because you can grow stuff on really compacted soils. You can grow turf. If you put in lime and fertilizer and a good sprinkler system, you can get a really nice green looking stand of turf. So the soil might look healthy from the surface, but just below the surface, it could be pretty close to concrete in some cases. Now, this is kind of a typical suburban scene. We put down the subdivision, the developers come in, they dig out a hole for the tree to go in, and they put a nice nursery stock bald root mass of tree in there. And it looks great to begin with, that you've got a 3-4 inch caliper tree right off the bat. However, in some cases, if you go to these subdivisions, even after 30, 40 years, you'll notice these trees haven't really grown all that much. So if you live in a spot that was developed in the 80s or 90s, take a look at your street trees and see how big they are. Have they been growing, or do they seem to be not much different than the size they were when they were planted? Some of this might be due to compaction. It's not in all cases, of course, but when you compact soil, not only do you squeeze out the pore spaces and make it less porous, you also create a really strong soil, a hard material. And sometimes it can be so compact and so dense that the tree roots just don't have the strength to push through that compacted soil. So it's almost like they're confined to that original hole that was dug out for this bald and wrapped tree to go into. And if the roots can't grow, the tree isn't going to grow either. So it may not necessarily die, but it may also just stay stunted like this. And I think this is a really good representation of that process. So this is downtown DC. This is Pennsylvania Avenue between the White House and the Capitol. And you see, I think maybe they're pin oaks. I'm not sure what species they are, but it's the same type of tree on either side, planted at the same time. These are probably 50 or 60 years old, at least by now. The trees over here on the left, you can see they're a lot smaller than the trees on the right. Well, why is that? Well, these trees were planted in a little tree box, and they have access to the soil. This isn't a closed tree box. They have access to the soil that's under the sidewalk here, and the soil that's under Pennsylvania Avenue itself on the left. But that soil underneath the sidewalk and the road is highly, highly compacted, which actually isn't a bad thing. You don't want your road sinking down, but it's a terrible place for tree roots to grow. Plus, there's probably not very much life going on in the soil in addition to the compaction, just because you've got this impervious surface on top, so oxygen and water is not diffusing down into it and feeding the microbes. So you're trying to get these tree roots to push through this highly compacted soil on either side, and it's just not working. So these tree roots are probably pretty much segregated into this little tree box that the tree is planted in. And because the roots are stunted, they don't have access to a good volume of healthy soil, the tree is stunted. These trees on the other side, I wouldn't say they're growing in great soil, but at least they have access to this strip of green between the building and the sidewalk, a good 30, 35 feet or so of open soil. Still probably fairly compacted soil, not particularly healthy, but obviously it's strong enough for those plant roots to penetrate through. And you can see how much healthier and larger these trees are compared to their stunted compatriots over on the other side. So that shows you how a good visual of how a bad soil will lead to bad growth, especially high urban soil compaction, and how that can stunt the growth of your desired species. When we develop soil, we tend to mix soil as well too. So we have those natural soil layers or soil horizons with the topsoil on the top, but during the construction process, all those layers get mixed together. And what happens is the topsoil, which was concentrated at the top, and maybe there wasn't much of it, may have only been 2 or 3 inches, but it was right there at the top where the soil roots had access to it, and right there at the top where it was easy to get oxygen and water into it. Now that topsoil, that A horizon, is kind of dispersed and spread throughout the soil column, throughout the depths, maybe in the first 4 feet or so. When this happens, it's not really topsoil anymore. It's not that it disappeared, but you need that concentration of biology in one spot, especially in the spot that roots have access to really power the nutrient cycling that's necessary for healthy soil growth. If the topsoil gets mixed and dispersed throughout all the other subsoil layers, it's just not going to be the same. So again, here's your sort of natural soil. And here's an example of what might happen to it after development. It kind of becomes homogeneous, and it's all sort of an equal mix because everything gets equally dispersed throughout the depth of the soil. Very importantly, when you have a loss of productive topsoil, you have a loss of microbes. Remember, the microbes tend to concentrate in those few inches of topsoil. That's where they really like to live. And you'll find microbes in other parts of the soil, but not nearly in the concentration and the numbers you'll find up in a healthy, happy topsoil A horizon. So the topsoil gets dispersed, the microbes tend to die out. Their numbers drop greatly. And if there's less microbes, there's less chance of that good organic matter and nutrient cycling and decomposition that you really want. So after discussing all these things, what can we think of a new concept of soil? Is soil really the intersection of the hydrosphere, the lithosphere, and the atmosphere? Is it really a mix of sand, silt, and clay? Absolutely it is, but those are sort of definitions, physical definitions of what the soil is, where we are more interested in both in what it is, but also what it does, what roles or functions it does. So in addition to that, we can say the soil is also a very rich and diverse ecosystem. It's a very complex food web. It's a great recycler of materials. We take all these things together. I really think of the soil as acting like the Earth's stomach, just like our stomach. In fact, it's very analogous to our stomach. We're finding more and more about the human stomach that it's full of foreign bacteria and other cells that are not human cells, but are working in concert with us to help us break down the food we eat and release the nutrients that we need into our body. The microbes get organic carbon, they get energy, and they release to us the energy and the nutrients that we need in order to live. Well, soil is sort of the same way. It's full of bacteria and fungi. They're breaking down that organic matter and feeding themselves while simultaneously releasing nutrients into the soil that is available for the plant roots. They're just doing it on a much larger scale than the human stomach. They're doing it all across the world. So if it is the stomach, how do you keep it happy? Well, just like ours, when we're hungry, you got to feed us. When soil's hungry, you have to feed it. What is soil food, though? Well, there's a misconception that soil food is fertilizer. It is not. Fertilizer has its place, and sometimes it's very, very necessary. We can over-fertilize, of course, it can be a problem, but sometimes fertilizer is absolutely necessary. But you shouldn't be fooled into thinking that it's plant food or soil food. It's not. It's basically a plant vitamin. We take our vitamins in the morning. They do great things for us as well, too, but you can eat a lot of vitamins and you're not going to get full. Vitamins give you nitrogen, phosphorus, potassium, lots of good stuff, but it doesn't fill you up. What fills you up? Organic matter, organic carbon. And that's the same thing with soil. It needs those nutrients, certainly, but it also needs organic carbon. The carbon or the organic matter is what gives the energy, not the nutrients themselves. Nutrients are very important, but it's the organic matter that fills you up and fills up basically every living thing on the planet, for the most part. So fertilizer is not a plant food, it's a plant vitamin. So what is a plant food? Well, anything that contains organic carbon. So this could be your compost. This could be other additions like manure. That's sort of kind of bridging the gap between fertilizer and compost, but of course it's got a ton of organic matter in it, so it is plant food or soil food. Milorganite, that's a bag to the right there. Oddly enough, that's manure too. That is Milwaukee municipal treated sewage sludge. And they've been selling it to gardeners and golf courses for over 100 years, I believe. I think it goes back to the 20s. It's good stuff, and you don't necessarily want to put it on your food crops, your vegetable crops, because it is sewage, but it's treated, so it's quite natural stuff. And it doesn't have to be something that you go buy, of course. There's been, plenty of the other speakers earlier have mentioned that you can just add the organic matter that naturally is at your house. You don't have to go looking for a product to buy. One great source of organic material is the leaves that fall. We do a crazy thing every fall. We rake up our leaves, we break our backs, we spend weekends doing this just to put it on the curb so somebody can come take it away, when what in effect we're doing is exporting organic matter off of our property, which could do great use on our property. And then some of us even go to the county landfill and get the leaf mulch, which was made by the leaves that we raked off of our lawn and our neighbors' lawns, and then bring it back to our soil and rake it into our garden beds. You can mow those leaves right in, even if you have a lawn. If you chop them up into small enough size, dime size or so, they'll settle between the grass blades and they won't smother your lawn, and they'll decompose in place and add a ton of organic matter to your soil, and that can help strengthen it greatly over time. It doesn't even have to be as complicated as this either. If you're mowing your lawn, just leave your grass clippings right on there. And that's another great way to recycle organic matter back into your soil. So it can be a fairly simple process, or it can be a little bit more of an intensive process, like these folks who have foregone their fall fertilization, and what they're doing is raking in already pre-made compost. They must have bought this from somewhere. You see them putting it up into piles, and they're going to get a crew out there or do it themselves. They'll rake these piles out into kind of a thin, even blanket, 1/4 to a 1/2 inch thick blanket over their entire lawn, which again is thin enough not to bury the grass, but it will allow that compost to be naturally mixed into the soil through the work of burrowing worms and other soil fauna over time. And that will add a ton of good organic matter and nutrients down into the soil and make that soil stronger, healthier, and happier. So when you feed the soil, you are powering up the soil food web. When you're adding this base material of organic matter, it's eventually going to filter its way up into the rest of the soil food web. And the soil food web is our great power source for the global nutrient cycle that occurs in soils. And the nutrient cycle is primarily powered by the decomposers, the fungi and bacteria and other microbes in soil that take that organic matter, break it down, decompose it, and in the process release nutrients, some of which get dissolved in the water in the soil. And when that happens, when they get dissolved, they can be taken up by the plant roots. When they do, the plants put on new growth. A well-fertilized plant with all these good nutrients released by the decomposers will put on new leaf mass, new shoot mass, new root mass. And over time, whether it falls directly back down onto the soil or whether it gets processed through our terrestrial food web, everything eventually, organic-wise, has to return to the soil. And when it does, those nutrients that were exported out of the soil get returned to the decomposers, where the decomposers will again break down that organic material, release those nutrients, and the cycle continues again. So you really boost up the decomposers and give them good food. The rest of the nutrient cycle will follow. And when you have a well-fed soil with a good nutrient cycle, a healthy soil food web with a big base of organic matter that's feeding those microbes and the rest of the higher levels of the soil food web, food chain, you have a resilient soil. A healthy soil is a soil that needs a lot less management. And a really healthy soil is one that replicates itself. It's got that healthy nutrient cycle going. The nutrient cycle creates healthy plants. The plants grow better. When they grow better, they're adding more organic matter back to that nutrient cycle, powering it, powering themselves. It's kind of a self-replicating feature. So a well-fed soil is a resilient soil that you have to do less with, that you have to manage with much less with a lighter touch to get the results that you want. So give the decomposers good soil food and let them do the work for you rather than doing the work yourself. And that is it.
Thank you so much, Dan.
Thanks,
and we have 9 minutes for questions. So that I'm just going to go through them really quickly here because there are several in the chat. Charlie, you were first. Do you want to ask the question yourself? And maybe Dan, you could stop sharing and then we can see each other.
Sounds good.
So my question was related to texture, structure, and organic matter. As you add the organic matter, is it going in between the macropores, and is that creating the greater water holding capacity, or is the organic matter getting mixed in with the micropeds?
A little bit of both. So earthworms are sort of nature's burrowers, but they're also nature's mixers. So if you're adding organic matter that you weren't tilling in, which is what most people do unless you're dealing with a vegetable garden or something, the burrowing organisms within soil will naturally incorporate that organic matter into the soil. So a lot of times you'll find a really concentrated amount of organic matter on the walls of earthworm burrows or other burrowing insects. And also in root burrows as well too, because those small roots are constantly growing and dying. So as they grow, they create their own little pore space or burrow as they push through the soil. And as they die, the organic matter decomposes and leaves behind a macropore. But those, some of that organic matter will get mixed into the smaller micropores as well. But yes, it tends to concentrate a bit more in the macropores and then on the surfaces of those soil beds.
Thanks.
Thank you. Debbie wants to know about treated pool water. Does that damage soil when she has to backwash her pool filter?
Um, if it has a lot of chlorine, it potentially could. I'm not so familiar with pool maintenance, but I know that at least in Fairfax County, what they say is before you drain your pool for the winter, to let it sit for a week or two so that the chlorine will evaporate off before you release it. That's more for water quality, so they don't want to get that chlorinated water down into streams and rivers. But I would imagine if it has enough chlorine in it to harm the streams and rivers, it probably wouldn't be good for our soil either. So as long as it is fairly low in chlorine, or if it's got a little bit of time to allow that chlorine to evaporate, it should be okay. The other thing we see with pool water is sometimes if it sits stagnant, it has a very low dissolved oxygen content. But generally speaking, if you let it run over the soil for a little bit, just that natural tumbling will get oxygen back into it. So I think chlorine is probably the big thing. If it's low in chlorine, I would imagine it would be fine. If it's high in chlorine, then I think it could do some damage to the soil.
Thank you. And what about moss?
Moss is only bad if you don't like it. There's nothing wrong with moss. Often moss is a sign of low pH in the soil, which is not unusual around here. Our soils are naturally acidic. So moss is an issue if you want to grow grass, because it probably means that the pH of the soil is a little low for grass, but that's something that can be fixed fairly easily by adding a little bit of lime. I would always recommend, though, do a soils test first. You can pick up a soils test kit from the Cooperative Extension or from the county library. You can send it off to Virginia Tech for, I think it's $12 now is the cost, and it'll tell you what your major nutrients are and what your pH is. So if you do have to revise the pH in order to grow whatever it is you're trying to grow, you know what you have to add, because if you're just guessing, a lot of times you'll get it wrong.
Cool. And Lorene, I'll ask the first part of this anyway, has brought in fill dirt from construction sites, which has its issues. And do you want to finish asking that, Lorene?
Sure. Yeah, I noticed a lot of the fill dirt was that clay layer, which is obviously a much deeper layer. In many spaces, I tilled in organic matter and have grass growing, but is there anything more that I can do to improve the health of the soil, particularly something that doesn't require tilling since there's already plants growing there, but are there things that I should add since I have a very deep layer that's now at the surface?
Sure. I'd say you just want to boost up your organic matter content. So kind of a simple but slow way to do that is grass cycling. So make sure that when you do mow your lawn, you're not taking the grass clippings off. You're just letting them lay and decompose. And then faster way to do it would be if you do have fairly decent tree cover. Instead of raking your leaves in the fall, you can mow them in. And if you have a mulching mower, it makes it easier. You usually only have to do one pass, but you can certainly mulch your leaves in with a regular lawn mower. You might just have to do maybe 2 or 3 passes. And you basically want to chop the leaves up so that they're about the size of a dime and can settle between the grass blades so it won't smother your grass. And that will pretty quickly get incorporated to the soil through the natural act of the soil fauna, the worms and other burrowers kind of taking that stuff from the surface and bringing it down into their burrows and their pores.
Thanks. And Daniel is wondering about planting trees in compacted soils.
It can be tough. One of the great terms I've heard is don't put a $300 tree in a $10 hole. So do the work early to make a nice big hole for that tree to go into. Sometimes it can often be easier to actually, you get one of those nice balled and burlap trees from the nursery, which can cost several $100s, and you get sort of an instant effect on your landscape. But often those trees really need to be babied the first couple of years in order to get them to grow, because generally they have a very small root mass for their above ground mass because they were grown in a container and then cut out. If you get a seedling, which looks very small and doesn't look like much for the first year or two, it often by the 4th or 5th year will be taller and bigger than that balled and burlap tree because it's in balance. It's got the right root mass for its size. So you might want to think about doing seedlings because then they're smaller. You don't have to dig as much of a hole. But if you are getting one of those bigger trees, put the effort into digging a really nice hole to leave plenty of space for those roots to grow. And oftentimes what I've seen people do is they dig out sort of tendrils, if you will, almost like tentacles from a squid or a octopus. So if you have rototiller, you can kind of radiate some tendrils out from your central hole, and those will become sort of the highways for the roots to grow, where they may have trouble pushing through that more compacted soil in your lawn. So that's one thing that you can do. And mixing in a little compost as well too, as you're digging your hole and planting your tree, can be helpful.
Thank you. And I'm going to ask Dell to ask part 2 of his question about moss, which he didn't get the first part. So Dell? No?
I'm sorry. I just realized you were directing this to me. I'm sorry, Dan, I didn't understand. I have completely cleared I have a beech forested yard, and I have completely cultivated a moss yard. So and I keep the grass out of it and the invasive natives, but I let the natives grow in a naturalized state.
Mm-hmm.
But I keep all the leaf litter off of the moss. And it's just occurred to me from your presentation that maybe I'm damaging the A horizon in the topsoil because I'm not feeding organic material. I'm not allowing organic material other than my little natives that are growing up. So what is moss bad for the A, whatever it is, the A horizon?
A horizon, that's a good question. That's a tough one. I don't think it's bad necessarily. I'm not sure. You know, if you have stuff growing on the soil, whatever it is, it's adding organic matter, because a lot of the organic matter that gets put into the soil is just exuded through the roots of living plants, whether it's grass, moss, trees, or native shrubs and perennials. So as long as there's something growing on the soil, there should be organic matter put into the soil. But certainly a lot of the organic matter that gets down into our local soils is that leaf fall. But with moss, especially since it's so low, it would be fairly easy to smother it with too much leaves. So
Okay.
I think as long as you've got the growth that you want, you can keep doing what you're doing. I don't think you're doing too much damage.
Okay, thanks.
Sure.
Okay, and we have 30 seconds left apparently. So I'm not sure if we can get through the last questions. Here's one. Should you create the various layers inside of containers for houseplants to increase growth? What about succulents? That's kind of, yeah.
That's a tough one. I guess it depends on the plants. For house plants, you know, we're dealing with such a different and controlled system. So it's a little bit different than the general rules we would have for plants outside in the natural soil. But yeah, you could, but you do have to, with those house plants, make sure that you're not overburdening the pot with too much roots, because they will obviously grow out of their pot at a certain point. You'll need to repot them, because the soil just needs access to a certain, the roots need access to a certain volume of soil. So just know if you do grow more, you might have to repot that plant a little bit sooner than you normally would.
Okay, and real quick, what about Japanese beetle grubs? Is there a good way to deal with things like that?
Well, generally, if you have a healthier soil, you're going to have those good native flora and fauna in your soil, which can help outcompete the invasives. And that's maybe a way to deal with it without having to